get so A is equal to V, and that means the x component of the velocity is V times the cosine of omega times T. Okay? That's the x component of velocity. How about the y component of velocity? Well, let's see. Let's use Vy at t equal to 0. Again, what did we say? The velocity, the y component at t equal to 0. T equal to 0 was just in the x direction, so there was no y component of velocity, so 0. So 0. So let's plug in 0 for t here. I get b times the cosine of, I get b times the cosine of phi 2. Okay? Of phi 2. Now, you got the product of two things is equal to 0. One of them is 0. Which one? Is it the b? Or is it the cosine of phi? The cosine of phi, you have to say the cosine of phi. Why? If you say b is equal to 0, that means the y component of velocity is always 0. But look at, we said there is an initial acceleration in the y direction. So there will be a velocity in the y direction a time t later. So the y component of velocity cannot always be 0. So b is not the 0. Okay? So b is not the 0. All right? So which one is the 0 then? The cosine. The cosine of phi. So if the cosine of phi is 0, let's see. So I get Vy is equal to, if cosine of phi is 0, it means phi is what?
1.
It's cosine of something gives me 0.
90.
90 degrees, pi over 2, or negative pi over 2, right? Plus or minus pi over 2. Either pi over 2 or minus pi over 2, one of them. So V will be B times the cosine of omega t plus or minus pi over 2. Okay, plus or minus pi over 2. But the cosine of something plus pi over 2 or minus pi over 2 shifts to a sign, either a positive sign or a negative sign, right? When you shift the cosine by pi over 2, you get a sine, function. So this is equal to plus or minus b times the sine of omega t. Okay, that's what we get. Now, this would enable me now to guess whether it's the positive. Should I take the positive or the negative? Well, think about it. At t equals 0, 0. A moment later, the y component of velocity, will it be positive or negative? In what direction is the force? Up. So it will give it some component that's positive. So that means I have to go with the positive. So it has to be positive. Okay? So I go with the positive because of the initial. So again, I'm going to erase this, right? So it will just be the positive. So we will go with the positive for the argument I just mentioned. So that's that. Now I need to figure out what b is. Now how much is b? Well, b, the claim is it's equal to v. B has to equal to v. Why? Well, let's omega t, as t goes on, at some point omega t will equal to pi over 2. At some point omega t will equal to what? Pi over 2. What's cosine of pi over 2? 0. So the x component of velocity will be 0 at some point. So when omega t is pi over 2, let's look at what happens here. Pi over 2 sine pi over 2 is 1, so I just get v. I get b. But the magnitude of velocity is always v, so b has to equal to v. Right? So I know I'm saying the argument orally, I'm not writing it. So for that argument, b is v. All right? So b has to equal to v. So I get b times the sine of omega t. Right? So let me just summarize those. We got Vx is V times the cosine of omega t, and then Vy is equal to V times the sine of omega t. Okay? So now, what's x of t then? Well, x of t, let's see. You need to integrate this to get x of t. Integrate it. What's the antiderivative of cosine omega t. Antiderivative of sine, that's sine. It's v over omega times the, well, x of t. Or you could do v over omega times the sine of omega times t. Yeah. Because derivative of sine is cosine. And for this one, y of t, oh, plus a constant, right? Yeah, plus a constant, let me call it, plus a constant, C1. Alright, and then y of t would be minus v over omega times the cosine of omega t, plus another constant, let's call it C2. Alright? Okay, right, because derivative of cosine is negative sine, so you need to put a minus to make it plus. Okay, we're almost done. It has to turn out that this C1 and C2 are zero. And we do that by the choice of origin. Have I chosen the origin of my system? I have not. So I would choose the origin such that C1 and C2 are equal to zero. I'm skipping a detail or two. So you can choose your origin such that C1 and C2 are zero. So by choice of origin, I get x of t will equal to v over omega times the sine of omega t, and then y of t equals to v over omega minus v over omega times the cosine of omega t. Yeah, that's that. Now let's figure out, this is uniform circular motion. Okay, this is uniform circular motion. How do I show that? You have to show the radius is constant, the speed is constant. You need to show that it's actually a circle. How do you show it's a circle? Square the x, square the y, add them together, take the square root, and show that that's a constant. So if I do this, I have r squared equal to x squared plus y squared. When you square this one, you get v squared over omega squared sine squared, and this one you get v squared over omega squared cosine squared. Factor out the v squared omega squared, you get sine squared plus cosine squared, which is what? 1. So this is simply v squared over omega squared, and that means the radius of this circle would be v over omega. But let's, what was omega? Omega is qb over m. So r will equal to v m over q d. That's the radius of the circle. The frequency of oscillations, the frequency is 2 pi, is omega over 2 pi. Is omega over 2 pi. The frequency of oscillation is omega over 2 pi. And because omega is 2 pi over the period, and 1 over the period is the frequency, so the frequency is omega over 2 pi. And omega is qb over m, so divide that by 2 pi, you get qb over 2 pi times m. Alright? So now, let's say you don't care about all these differential equations, and what do I want you to know? I want you to know that it's a circular motion, it'll be a circle. The radius of that circle is mv over qb, mv over qb. And then you can say that the frequency is qb over 2 pi m. Once you know this one, you know this one. Okay. Yes?
And just to clarify, so off the graph, like v sub x is 0, you said v is equal to a because the magnetic field doesn't do work, so the velocity doesn't change?
Yeah.
Okay.
The speed never changes, yeah.
You said once you know this one, you know.
I said, if you know that r is equal to mv over qb, you can derive this one.
So,
Because the frequency is the speed over 2 pi r. Okay. So why did I do this? Well, almost every book skips it. What they do is they just say, well, it looks like circular motion, therefore it is. It's not pretty satisfying. It turns out it is, but, you know, that's not good enough. All right, so that's what you need to know, that's about it.
This is circular motion?
Huh?
Uniform circular
It
motion?
is uniform because the speed doesn't change, and it's circular, yeah, so it's uniform circular motion, yeah. So I need to erase these two boards to get us into the next chapter. Okay, I will, I might mention one more, yeah, okay. I might mention one more thing about dipoles, since you might need it for the homework. So let me just mention that before I put a closure to this chapter. So, yeah, so let me, can I erase now this side?
Yeah.
And pretty soon I will need that one, so please, make sure you get the other one. Yeah. Okay.
There is a problem. This is the radius. Okay, this is the two equations.
So, magnetic dipoles. Remember electric dipoles? For an electric dipole moment, it was, if you have a minus and a plus, right? And they're separated by a distance d, right? Or x, I forget what I think it was b. And this one is plus q and this one is minus q. The electric dipole moment was just as magnitude of q times d, right? If you put it in an electric field, it will rotate. It will experience a torque. And you may remember there was also a potential energy associated with it. It was U, the potential energy. It was minus P dotted with the electric field, right? Dotted with the electric field. And the torque was the dipole moment crossed with the electric field. And I think we spent like 2 boards deriving this equation here for the electric dipole. Magnetic dipole moment, similar behavior, but a different definition. So take a current loop, so for this is electric dipole moment, right? So magnetic dipole moment take a loop. Here's a loop of radius, let's say r, right? Radius r. And let's say the current is going this way. There will be a magnetic field in this direction on the axis of the loop. Okay? And if the current that's running here on this dipole, on this current on this loop, if there's a current like this, there will be a magnetic field this way, and we associate a dipole moment with it. And we say the direction of the dipole moment is in this direction, and we give it the symbol mu, the magnetic dipole moment. That's the symbol mu, and its magnitude is the current times the area. So in this case, the area is pi r squared, so I times pi times r squared. That's the area. Okay. Its direction is always perpendicular to the loop.
Doesn't matter if it's clockwise or counterclockwise?
It does. If the current is this way, it's the direction is going. Direction of the magnetic field. Yes. So if you orient your thumb with the current, the magnetic field will be coming out. Yeah. So now, what's the potential energy and what is the torque on it? Very similar behavior to this. I will not spend time to derive it because there is more important material. And so here is the potential energy associated with it. It's exactly, just by analogy, it looks like this. Minus, instead of P, it's mu, that's the dipole moment, dotted with the magnetic field. And the torque is mu crossed with P. Okay, mu crossed with P. And of course, the magnitude is mu times V times psi. Okay, for the torque, right? Magnitude. that puts an end to this chapter. Chapter 29 is done. Let's go to chapter 30, electromagnetic induction. Now in chapter 30, it comes from experiments. So people figured a changing magnetic field will induce an electric field. So if you take a coil, let's say here's a coil, like this, and you put a, let's say a light bulb here. This is a light bulb, this is a coil. If you bring so the light bulb doesn't shine, it's not shining. If you bring a bar magnet, doesn't matter which one is the side. So let's say this is the north, this is the south. And you quickly get the bar magnet into the coil, the light bulb will shine. If you leave the magnet inside the coil and not move it, the bulb will not shine. If you remove the magnet quickly, the light bulb will shine. If you bring the magnet slowly, the bulb barely shines. So, experiments basically show a change in magnetic field will induce an electric field. And we want to understand, so there will be brand new physics, but at least in the first part, we can understand it using the QVB force, and then in the next time we will get to the one we cannot understand. So, here's let's start with the following. Take a rod, here's a rod. Okay, here's a rod. This is a rod, okay? Conductor, it's a conducting rod. And so, imagine you're in a region where there is a magnetic field that's into the void. I will just draw enough of these. Alright, so the magnetic field is into the void everywhere. Okay? Now, if you leave the rod here, nothing happens. Why? Well, remember, magnetic forces only act if you're moving, right? If the charge, remember magnetic force, FB? What was it? Q, V cross V, right? Otherwise, if V is zero, the magnetic force is zero. So nothing happens to the charges. So what you do is this. Let me draw some more magnetic field. What you do is you pull the rod. You come in and you pull this rod, drag it this way with some velocity. With some velocity. You drag it to the right. Is that clear? So the rod, every piece of the rod is moving to the right. So what happens? Charges are moving then, right? If every single piece of the rod, including the charges that make up the rod, the atoms and everything, so they're moving to the right. So imagine you're a plus charge. Imagine you're a positive charge and you're here. What happens to you? You're a positive charge and you're being dragged to the right. So you will experience a magnetic force. In what direction? Your velocity is to the right. Magnetic field is in. Up. Yes, upward. Velocity is this way, magnetic field is this way. V is this way, magnetic field this way. If there's a cross product, this way, yeah. So if you're a plus charge, you will go this way. If you're a minus charge, you will go down, right? So pretty soon, here's what happens. So a little bit later, so this is, as you drag it here, there will be pluses here, and there will be minuses here. Pluses and minuses. Okay? Is that clear? So does this process go on forever, or it stops eventually? It will stop eventually. Why? Well, you're trying to pile up more positives on here, but the positive says, sorry, we had enough. We're setting our own electric field now, so that these pluses will set an electric field down, right? If you have pluses here, minuses here, electric fields go from plus to minus. The magnetic force is trying to push them up, but the electric force is pushing them down, resulting in a net force of zero, right? So the electric force and the magnetic force will have will have an equal magnitude when this process stops. So when does it stop? At equilibrium. At equilibrium, the electric force equal to the magnetic force, equal to the magnetic force. The electric force, as usual, it's the charge times the electric field. And it's downward, but if their magnitudes are equal, they will cancel, because they're in opposite directions. QE. The magnetic force has magnitude Q times V, Q times V times B. Q times V times B. So, cancel the Q, so you get the electric field will equal to V times B. That's the electric field needed to cancel this.
V as mean the velocity, the rod.
The velocity, yeah. The velocity, yeah.
If the rod doesn't move, that means there's no force is not force.
Yeah, if the rod stops moving, the charges will soon will merge together and you just get a zero. They're not polarized anymore.
So
Yeah.
it will go back to the stable
Yes.
position.
Yes, it would be just a bar.
So
That's not.
if it's when it's moving, the positive charge negative charge goes by and by, right? So when it's moving,
Yeah.
the positive charge goes down and up and down, and negative charge keeps moving, right?
Positive charges will go to the top, minus charges will go to the bottom.
Also, if it stops moving, does positive just go down to the bottom?
Oh, yeah, the positives will, well, you would have some negatives go up, some positives go down until it's neutral again. It's not polarized anymore. So you cannot just have, you would have equal amounts of pluses and minuses everywhere. So it's, the net will be zero, yeah.
So FB comes from you constantly
Yes.
pulling on the bar.
Yes, you're the one who pulled it to give everything a velocity, and then the magnetic field will pull the charges down.
So as soon as you let go, it'll go back?
It will go back, yes. I mean, it would take a small amount of time, but it will go back, like 10 to the minus 12 seconds or something. Very tiny amount of time. So that's that. So now the question is, while you're pulling it, and it's polarized like this, what's the potential difference between the top and bottom? What's the potential difference between the top and bottom? So, let's say the rod, here's the rod again. There are the pluses, there are the minuses, and let's say the rod has length L. Has length L. The potential difference, delta V, the potential difference, or the potential at the top minus the potential at the bottom will equal to what? Remember, it's that integral of E dot dl, it's like this, negative the integral from 0 to L, like this is 0, this is L, of E dot dr, right?
The volume?
Huh?
The velocity?
Which one? This is voltage, potential difference. Yeah, this is voltage. So now the electric field is just V times B. It's constant, right? There's a constant value. So you can pull it out. The direction is in the negative Y direction. So you will get the following. You will just get this. The electric field, which is VB, times the length of the rod, which is L. And we usually just write it as B times L times V. BLV. That's the potential difference between the top and the bottom. Okay? Okay. So, quick example. Okay. So here is a quick example. Let's say you have an airplane flying, right? Flying. So here are the wings. Okay, so there's wings. Plane, oops, something. Sorry. So some airplane flies, and you got the idea, right? Those are the two wings of the airplane. and the plane is going like this. Let me just draw the two wings. This is supposed to be two wings of an airplane. And let's say the airplane is moving this way with some velocity. Let's say the velocity is 260 meters per second. Okay. Now, as the airplane flies, there is a magnetic field. Magnetic field from who? The Earth, yeah. So suppose it's in a region, they say here, around northern Canada, the magnetic field will just be straight down. And it goes from the South Pole to the North Pole, and at some point it's like pointing straight down. So the magnetic field, let's say, is straight down. Okay. The wings of the plane, they have a length, wing to wing, about 65 meters. 65 meters. And they say there is a potential difference between the two wings. So the magnetic field is down, I'm sorry, is into the board. The velocity is this way. So which side will be positive and which side will be negative?
Yeah, positive is gonna be on.
Good. The positives would be on the left, so it would look like that, right? The velocity is this way, B is this way, so QVB would be the other. So this side would be negative. So this would have a higher potential than this. They're saying this: if the potential difference between the two wings, between the left wing and the right wing, is 0.95 volts, find the magnetic field in that region. Find B. Now, we know the magnetic field of the Earth is half a Gauss, 0.5 times 10 to the minus 4, or 5 times 10 to the minus 5. That's what we expect it to be. But we need to calculate it. I expect it to be of that value. So this is exactly this situation. I mean, this one, the rod was moving this way, and the magnetic field was in. In this case, the rod or the plane is moving that way, the magnetic field is in. So it's the same situation. So the solution, we use that. We got delta voltage is the magnetic field times the length times the speed. I put a little curly V, so to emphasize it's not the voltage. So the magnetic field will be delta capital V divided by L times the speed. They said 0.95 for the potential difference divided by L times V. The length is 65 meters, and the speed is 260. And this turns out to be 5.6 times 10 to the minus 5 Tesla. That's it. Okay. While we're here, one more question with this. We're going to do one more question. And not going to be as simple as this one, but let's see if you understand what we can do. Oh, I should have, that's okay. Stop the recording and start it again because we started a new chapter. Otherwise they get mixed. That's fine. All right. I'm going to erase here. I hope you already got that. Did you get this one? Yeah. So the next question, the rod is not going to be just the rod is not going to be just be dragged like this. Okay. So here is to make it better. We're going to make our rod go in a circle. Okay. So what does making it go in a circle? See, if you drag it, every single piece is moving at the same speed. If you drag it like this, but if you rotate it, which one is moving fastest? The edge. Yeah, and then so they progressively move slower and slower till this end. So it's different speeds. So let's see what the potential difference in that case will be. Yeah. magnetic field is still into the board, okay? Magnetic field is still into the board. You have a rod. You hold it from here, from the end, and the rod spins with an omega. Spins with an omega. It is rotating at an angular velocity omega, and the rod has length L. So first, which side would be positive and which side would be negative? You know what, let me spin it this way. Sorry, it's not gonna matter, but I'm going to spin it this way, just to have which side would be positive?
This side?
This side would be positive?
Yeah.
Okay, well, let's see. Let's say you take one charge here, it will be moving this way, right? That's the velocity. Okay. Magnetic field is N, so V cross V will be this way. So yeah, so a positive charge will be pushed toward this end. Yeah. So yeah, this side will be positive, this side will be negative. Okay. So first, we know that the speed V would be omega times R, right? Speed is omega times R. The magnetic force would be Q times V times B, right? QVB. Forget about sine theta, it's 90 degrees, so sine of 1. Sine of 90 is 1. That's the magnetic force. Magnetic force will try to push the charge, the positives that way. Now at equilibrium, there will be an electric field to oppose the magnetic force, and so it will be toward the center. So at equilibrium, let me write, the electric field is always charge times the electric field. At equilibrium, we have the electric force equals to the magnetic force. And that means QE equals to QBB, which means the electric field is just B times B, right? Or V times B. But the speed is omega R. So electric field will be B times V, but V is omega times R. That's the electric field at each point. Okay? So it's not a constant electric field, it's non-uniform. And that's needed so to cancel the magnetic force that's not uniform. So delta V change the potential difference between the one end and the other. I know the right end, that end would be positive, it would be at a higher potential than this one, so just integrate. It would be the integral from 0 to L of E times dr. Of E dr. Technically it's E dot dr minus integral, but E points in the negative R hat direction. It turns out to be positive. So integrate, you got the integral from 0 to L, V omega, that's constant, V omega. And then you have here R dr. Integral of R is R squared over 2, evaluate between 0 and L, so you get this, the potential difference delta V would be 1/2 of V omega times R squared. Potential difference between the right, the farther end and the closer end. Okay. All right. Now we want to get some energy out of this. I mean, dragging the rod, polarizing it, good, but we need some current to be flowing. Yeah. L squared. Yes, thank you. Yeah, L squared. Yeah, because we're evaluating from 0 to L. So you got the pluses here, the minuses here. when they get to the end, they're stuck to the rod. They don't just jump off the rod. Unless you heat them. But they just get stuck there. So you don't have a current, they just get polarized. So to make a current, people came up with the following apparatus, and that's the one we're going to look at for the next, let's say, 10 minutes or so. So here's the apparatus. You have rails like this. Okay? And these rails, they can have a rod that you can slide. So this rod here can be moved within the rail. Right? The rod can be moved within the rail. And you can put a resistor here if you like. You can put a resistor here. By resistor, I mean a light bulb, something, some energy consuming. All right? So let's say our magnetic field is still into, right? Into the board, everywhere. So what we will do is the following. We will drag this rod this way with some velocity v. And let's say this is the x direction, this is the y direction, and the z direction is that. We're going to drag it. So as you drag it, what happens? Well, as you drag it, pluses will go here. But now they don't get stuck here. There is a conductor. And they can move. Are we clear? There's a conductor. So plus moves here. There's no reason for it to just get stuck there. It can move. And so you will have a current. You'll have a current. This one. Those are lines. So you have a current. So the charges don't get a chance to pile up, actually. They will always move. So one question is, well, what's the power delivery to the resistor? Right? What's the power delivery to the resistor? And what is the current and so on? So let's see. So as we drag them this way, there will be a potential difference from this end to this end. Okay? It's like you have a battery, but it's not really a battery, it's you moving something. So what's the potential difference between this end and this end? We just did it. It's
This one?
BLV. BLV. So there will be a potential difference, B times L times V. That's the potential difference. I'm going to call it the EMF. Okay. Now, it's like you have a battery here. And a resistor hooked to a battery will experience what kind of current? What do we know? We know from Ohm's law, the voltage is equal to IR, right? Yeah. IR. So the current will be B L